Any of the recording, sharing the screen. Okay, so we're sharing the screen again. I don't even remember where I was. Yeah, so we were looking at the homework. We were looking at ONNX. Answer section 1. Yeah, here. Okay, so we were in this link. So I explained to you guys that you look at this Jupyter notebook to export the model, right? So that's done. I also showed you that I just put in the link here so that I can access conveniently the website. And then if you notice, what you will need is these two files. So you will have an index.html file this is just like web development, and then an index.js file, okay? And very simple. And then also the model that you exported. So you can see I have several .onix files, but you would just have one, for your homework, for the regression, and another one for the classification. Make sense? All right, so now let's take a look at these two files. Should be pretty straightforward. Index, it's just a normal index HTML file. What's the key thing here? Notice you import some JavaScript libraries that are related to ORT. You see this ORT.min? That just means ONNX runtime web. So just use that same thing. And then you have like an index.js file, which is the one that I'll describe in a second, which will have a function so that when you press the button, you load the file and then you process it. Okay. The key things that you need to have here are the text boxes, right? So you can see the text boxes here and a button so that you can collect the data. Usually you want to use some names, like box 0C1, box 1C1, and so on. And then once you press the button, notice that it's going to, on click, it's going to invoke a function called run example1. Got it? This run example1 will be defined in the JavaScript file, and it'll include some code that allows it to handle ONNX runtime, essentially. All right, so that's basically it. And then, of course, you will need to have some kind of a div or something, such as this one, predictions, so that once you give some inputs to the model and the model does the prediction, then those predictions can be displayed back onto the screen, as I did when I pressed the button. So you send it to something like predictions1. Any questions on that, guys? Does this make sense? All right. And then the next thing that you want to look at in run 10 is you want to look at the index.js file. All right. And this is a much more complicated file because I have several buttons and several input boxes, but you really can focus on just one of these. Okay. So for instance, the first one. So it should be, you can take a look at actually this one, like this one that says Lapine here. So run example1, this is the function, just use this exact same syntax. Notice that you create an X float to array, and then from the page, you grab all the text boxes and you load them into this X array. Do you see that? So I think in my example, I had about 7 values, right? So I create an X that will hold 7 values. Then you convert this into using ORT into a tensor X. Then you're going to have this try catch here. And if you notice, the first few lines are essentially bringing in the ONNX file. So you notice here, inference session.create, and you import the ONNX file. So the model, that create a session, and then you session run with the input TensorX. Do you see that? So at that point, you're giving it the data in the text boxes, and then you get the results. And then everything else is just about displaying those results back onto the website. That's it. Okay. Any questions on this one, guys? No questions? All right. So you will have to do this twice, right? You'll have to do this for the regression model and then also for the classification model. So find a data set, train a model, measure performance, and then deploy the model and build these little websites just so that you can, in real time, give it some inputs, get some outputs. Yes. Two websites is fine. Keep it simple. So remember, you're doing two phases of machine learning, the training phase and the inference phase, right? So the training is where you get the performance and you export the ONNX file. The inference phase is where you take that ONNX file, load it on this website, and run it. The only limit to this is that GitHub pages or GitHub doesn't allow files bigger than, I think, 25 MB. But this is very efficient, so the model should be much smaller than 25 MB. If for some reason you want to build something bigger, you can put it on something like Hugging Face's, hub, and then link it from there to here. Got it? All right, so it seems like this is pretty clear. The last thing I will show you is GitHub Pages itself. Okay, so how does that work? So here, for instance, I'm logged into my GitHub. So you can build any kind of static website on GitHub. It's got a functionality called GitHub Pages. So go to this one, this is the one for that example. Click on that. And then what you do is once you're logged in and you're in the repo that you want, you can just do it for the whole repo. You go to settings. See that? Just click on settings. Very easy. And then at the bottom, you'll see this link that says pages. So you click on pages, and then that's it. You don't have to have a domain or whatever. It's just going to use your GitHub account. So all you have to do is change this to main and click save. That's it. Once you do that, it'll take a little bit. It takes like maybe 5 minutes for GitHub to update it. But then after that, you will be able to reach the folder just by using this URL. So HTTPS, obviously, whatever your user is, .github.io / the name of the repo. And that's it. So you just have to put the index and the JavaScript files in there and do those two steps that I mentioned. And you're good to go. Got it? Any questions on the homework? This is homework 3, as I said, and it's due, I think, in 2 weeks. All right, so go ahead. Bright space. So I need to report in. Right, you put the code because you're going to deploy it and you want it to actually work. But then just do a report with screenshots showing evidence that it works and prepare the report and submit it. What you did, your performance metrics, so remember the whole process is taking the data, doing the correlation matrix, training. I want to see the losses. Then once I see the losses, you're going to evaluate on the test set, and you're going to say R square was 70 or something. So I said in the document, so if we look at I close this thing again. There it is. So if we go to the homework assignment again, yeah, R square is essentially the one I will be looking for. Yeah, so it's here, right? Your first neural networks. No, usually this is just my preference. So for regression, I'll prefer R square. And then of course for classification, you use the other metrics. Yeah, I wrote them here. So regression, I wrote R square. For classification, the F measure, the correlation matrix, etc. So that function I gave you prints them all. So any other questions, guys? Is this clear what you have to do? Yeah, so that's homework 3. There may be 2 more homework assignments. There will be one related to images and CNNs and so and probably a stable diffusion one, but those are coming up. Nothing else? All right, great. So that's homework 1. All right, now let's talk about the term project, which I'm pretty excited about. I have a pretty good one, I think, this semester that will challenge you guys. So let's take a look. So let's go to content. Yeah. Yeah, go ahead. CPU could be enough for it, I would recommend data sets that have like 4,000 to 5,000 samples, 20 features. Remember, if you did something like images for the classification problem, I can't input the pixel value of 784 pixels, right? So you would have to create then code to load an image, convert it into the tensor, and do it, which is totally doable. And actually, I have tons of examples in my GitHub of it if you want to do that for the classification problem. I have no problem with that. But otherwise, a simple classification, right? Like, what's an iris? Iris had 4 input features to predict 3 classes. So just don't use any of the data sets that we've done in class already, obviously. Though find some data sets. Yep, but you don't need a million. So for this assignment, yeah, you're right. You can do it with CPU. Nope. And I haven't, it doesn't, like I said, keep it to 5,000 samples, 20 features. So you can go to UCI, the UCI database. It's a university, and they have a ton of data sets there. You can go to Kaggle, there's even more data sets. Yeah. So I'm leaving it open-ended. This homework assignment, I don't want it to take too much of your time, as we have other things that I think are very important that we cover. But at the same time, this is a critical thing, right? So you need to tell, if you don't understand these topics, which are the easiest this whole semester, you really need to tell me, okay? Because I expect you guys that this is, after the GPT, this should be trivial, okay? But pretty important. Any other questions on homework, on this homework assignment? Pardon? Well, I mean, it's supposed to be trivial in the sense that obviously the GPT had way more going on as far as architecture. We did a linear regression in one of these examples. We did an MLP, and our neural network had 2 hidden layers. That's what I meant. The architecture is super easy. Everything else you should notice is exactly like the GPT, right? So the GPT was just complicated really in its architecture. Yeah. And that's what I mean by easy. I mean, it should be something, you should start at this point, you should be seeing this pattern that is very, hey, this is the same loss function I've been using all semester. This is the same, this and that. Got it? All right, great. Any other questions, guys? All right, perfect. So now, term project. Okay, this should be a good one. I've created a project this semester to challenge you a little bit. And I think also this will be a little bit different in the sense that you have to get in more into the code and not the data processing, but the actual machine learning. Okay, so this is going to be pretty interesting. I do still need to do this lecture. Okay, so that's this lecture I will do of this technique. I'll probably do next week. Okay, but let's take a look at the project. So I usually put the project on the very first module where you see this thing called ABET surveys. So you click on that. The project is usually the thing that's just before the final, right? So it's due the week before final. So that's when you're getting ready to submit. You will submit here. and you should fill out the surveys, essentially. So that's why I put it here, because it's towards the end of the semester. But this is the project, so let's take a look. We're going to click on it. I'll just read the description. I may add more information to this later. I haven't added links, but there is a module somewhere below that has all the links, okay? And that you shouldn't get confused. All right, so here is the project. So, what's different, obviously, this is homework assignments are individual. This is a group project, okay? So you can work with other people, so here's the description first. This is your semester project. Form groups of no less than 2 and no more than 3. You will need to present this project the week before finals, so week 16, and then week 17 is final. Okay, that's your when you need to present it. So this one you do need to present. You also need to prepare and submit a report as usual. I need to have some evidence of your work and so on. So what is the project about? The project is about using neural input optimization, NIO. This is a new technique, right? So you're kind of at the cutting edge here, and you'll be learning something very interesting that not many people are using in machine learning currently, but it's very powerful. So a lecture will be provided on this technique. So I will be doing a lecture coming up, and there's a paper that I might be sharing. But essentially, I'm going to tell you what NIO is. But essentially, in NIO, you train a model using regression data, right? So imagine you have some regression. You could use classification data, other stuff. I'm just saying as an example. But essentially, in NIO, you train a model using regression data. You then freeze the weights of the model. Okay, once it's trained, you freeze the weights of the model. And then use constraint optimization to figure out inputs that generate desired outputs for that model. Backpropagation is used still. So backprop updates the values of the input itself. You know how we have a model, we train it, and what is backpropagation doing? We give it an input, it goes forward compared to the real, pred to real, calculate the loss, and then use that data and backprop to update the weights, correct? Well, as it turns out in PyTorch, you can update other things. So what we can do is we just freeze the weights of the model, and the backprop goes all the way back to the input, because all we have to do is make the input that requires grad. And by doing that, actually now the input can be optimized. Do you see that? So this is what I want you to do. I want you to explore this idea, okay? So backprop updates stuff, and I'll give you like a scenario. And obviously I need to do a lecture, and I have code and things like that, but that's going to be next week. For now, I just want you to kind of start forming your groups and start thinking about problems you want to solve. So backprop updates the values of the input itself. More to come. You will need to find a use case and perform all the correct research, development, and evaluation. If you do a good job here, you could publish the work. It's novel enough at this point, so I keep that as a consideration. Any questions so far? So key thing, find somebody you want to work with, no more than 3 people, form your group, and you have plenty of time, I think. I mean, we're currently on week 10, and you have until week 16. So you have 6 weeks. That's plenty of time for this one. Also, this will allow you to not just use code as I provide. You will need to get in there, mess with the architecture, but also the loss functions now have to be it's something you have to manipulate. So you're not just going to be using, pardon? What? Yeah. The loss function, yeah. So like MSE and cross entropy. So you will have to manipulate that loss function a little bit more this time. Do you see that? So that's something so that's going to make it very research focused. It's harder. This is going to be harder in this point of view, but also interesting. Okay. Yeah, so that's the project. Any questions about the description of the project? All right, great. So now let me show you where the materials are going to live. I'm still updating this. So this is a new term project this semester. So let's take a look. So let's go to table of contents. Okay. And if you can see here, we're basically done with this today. Cross entropy, we're done with this today. I still need to cover loss functions a little bit more. There's some mostly theory, performance metrics, mostly theory, and then differentiation, mostly theory. But actually, these things tie to this really well. So here is, I added this new module. It's called Neural Input Optimization. You click on this NIO, and it'll take you, as you might imagine, to the repo that I have on GitHub, where I have, definitions, links, very simple code examples, and some project ideas that you can consider. Okay. So if you're interested in getting started with a project like this week, start reading through this. Okay. All right. So now let's think about NIO. Like, why would you use neural input optimization? Like, what's the point? So as I've said, you freeze the weights of the model. So really the thing that you want to optimize is the input itself. So maybe the idea is, think of it in like the most classic example I can give you. You're working at US Steel, right here in Gary Works, right? And you have a steel furnace, right? And so the steel furnace, imagine you're the operator and you do this to a whole bunch of valves, right? And then materials come in and temperatures go up and all that. And then something happens in the furnace. And then after a while, you have an output. And the output can be measured by another set of variables. So you now get steel. And the steel that you get this time around had a production rate of so much, a brittleness factor of so much, or a hardness factor of so much, a weight, a density. Do you see what I'm saying? So you describe all of that with, say, a vector of 6 values, right? And you could have done other things. Like when you're doing in the input section, you're saying, well, today I want to use 300 of natural gas. What does that produce? What is the production rate of that? Now, what if I want to use not 300, but 100 of natural gas? Do you see that? What does that produce? Do you see what I'm saying? So that's essentially the idea, okay? So you will obviously need to have, first of all, a data set of inputs to outputs, right? And you train a model in the normal way. And this is like a multi-input, multi-output regression model. You train it. So find a data set. Once it's trained, okay, then it's like that model has captured the physics of whatever that process is. Given an input, I get these outputs. So now the key is you have a different question. What would be the settings that I have to give it input to get an output? Got it? But what the great thing about this is you're using stochastic gradient descent to provide information to optimize. So think of it like this. A vector, so you have the model, the weights are frozen, the input goes in, right? And it produces an output. You have a set of constraints over here. Instead of having predicted and real data, what you have is predicted and what conditions does this meet? Do you see that? And so, for instance, let's say there's 3 variables, right? And the 3 variables are like, let's say, density. So a simple thing is the density greater than 150? Is the production rate greater than 1,000 for whatever reason? Do you see that? So you give it an input, and this input is what? What do you think? It's random. You actually start with a random input, and you run it through the model. It produces a vector. That vector with 3 variables, you say, is production rate greater than 1,000? is density between 200 and 500? If it's not, okay, that's fine, but that's represented in a loss function. So then that back propagates to the input, and now the input is going to be what? Via stochastic gradient descent, no longer random, it's updated to a better input. Then that new input goes through the model, produces another vector. Is it greater than 1,000? Is this one between 200 and 300? No, but it's probably getting closer. That optimization back propagates again until after repeating that 1,000 times, guess what? You produce an input vector that goes through the model. When it is compared, the production rate is indeed greater than 1,000. This other variable is between 2 and 400, so you've met the constraints. But the beauty of this is this input vector is now the set of values that you want. Do you guys see that? Does this make sense? Let me give you another example, the stock market, right? Or the economy. Let's say that you want to know about the economy. So you find a whole bunch of data about the economy, multiple inputs to multiple outputs. You train a model. You freeze the weights. Boom, that captures like the physics of the economy. All right, great. Now what do? I want to know next year, what do I have to do this year, right? So that next year, let's say the inflation rate is 2.5, the stock market is at, I don't know, 5,500, whatever, the S&P. The average home price is 250,000. Do you see that? That's what I want. Okay, given obviously that was in the data when you train the model. So now you start the process again. Grab a random input, run it, it produces a vector, compare it to those values, back propagate, and you keep doing that until it gives you an input that when that output comes out, I reach 2 point, it may not always hit the 2.5, but it might be like 2.6 inflation. And S&P is not 5,500, but 5,600. And what was the other thing? The housing price, maybe that one's 300,000. So not perfect, but as close as possible. And the key thing is all of that is being back propagated to the input. Do you guys understand how it works, how NIO works? Now, no? Do you have a question? So yeah, you train a model first, right? The normal way. And then you use stochastic. I will do examples next week. And then the goal here is to use backprop, not to update the weights of the model, because that's already trained, but to provide that feedback to the input. So you want to know what input, so that way you could make decisions today, right? All right, I'm going to invest this much in the stock market because this is going to give me that in the future. Yep. The weights, initially you grab a data set, you train the model, the weights get updated. In the second phase, you freeze the weights of the model, and you just have the model given an input vector of, say, 8, predicts a vector of 3, right? But you want to know what set of conditions in the input would give you this set of conditions in the output. Do you see that? But now you don't compare those outputs to real data per se, although you could technically. Instead, you compare it to constraints like, yeah. You have the goal of the outputs that you need, which is usually going to be, I want always inflation to be greater than 3. So here you just say, there's ways, I'll show you, ways that you can create a loss function that says, okay, this is greater than 3. And then that loss is computed so that it can be used to back propagate via stochastic gradient descent to the input itself. Then that random vector gets updated so that in the next phase, it's a little bit better. And the whole point is that you're optimizing that input until the case where you get a vector. Another way of thinking is forget stochastic gradient descent. You have a quantum computer, right? You want to get this vector in the output. Give it 1 trillion inputs, one of them will be closer to the output. Do you see that? And that input that gets you closer to the output is the right one. But obviously that we don't have that kind of computer. So we have to smartly figure that out. And that's what stochastic gradient descent does for you. This should, in fact, help you to understand stochastic gradient descent a little bit more as well and what it's doing in the background. Any other questions, guys? As I said, I will do a lecture next week and I will provide some examples. This, in fact, already has a very simple script of how it works. So you can start looking at it and playing with it. Now, what do you have to, so the thing is, oh, and I want to say this, the third thing is, I actually think you can also use images here. So for instance, think of it like this. You could give it an image to produce another image. That's possible. So initially, you know, the question would be like, what would my input image be to, you know, generate this type of image? Like maybe it's like a house and you want to make it into a haunted house. Do you see that? So you start with, you know, a random vector. It's going to do the process until that house is, you know, if this is a spooky house, this is a house similar to that one, but not spooky, for instance. You can imagine how there's lots of applications to this. And that's why I'm leaving that to you. You can pick the use case. Regression examples are probably the easiest, but if you want a challenge, possibly images, possibly other things could be worth considering. It doesn't have to be a big data set. You know, obviously for the training, the initial training before the NIO, you know, a good decent sized data set. The NIO does not require a data set. Instead, the model's already trained. You're creating random vectors that where the output comes out, you just compare it to a set of conditions. Like for instance, is it greater than 1700 or? Initially, you do need a data set, yes. So it's a two-step process. First step is exactly what you guys have done, right? You take inputs and outputs, you train a regression model, boom, normal. Got it? And the only difference is it would be multi-input, multi-output. Do you know what I mean by that, right? So instead of just predicting one regression value, predict a vector of like 3 or 4. Okay? So you need that kind of a data set. Once that's done, then NIO comes in where you freeze the weights of the model. And now your goal is to figure out inputs that would produce outputs that meet certain conditions. Yes, exactly. That's why I said the model models the physics of your problem. If it's a furnace, you're capturing how heat transfer works and all that stuff. If it's the economy, then it handles the behavior of the economy. Obviously supply and demand is in there somehow because the data set captures that. Right, exactly. So you would have to have some house data, build it, but then you use the model to figure out how to obtain an input that, given this model, produces an output that you want. So you have to it's up to your creativity. Yeah? Okay. So I'll give you an example where we also used it for generating passwords and things like that. So that's another example that I can give you. As I said, I'll show you the methodology probably next week. We'll do some examples of how it works. And then I leave it to you guys to pick a topic. If you like art, go with art, right? If you like the economy and the stock market, go with that. Whatever you want. Or a very intuitive set of cases is industrial production, right? So a chemical plant. Obviously, a chemical plant, you do this, right? To the machine, stuff goes in, and then output comes out that you measure. So now you want to know. So for instance, as an example, how do I make steel that's real? Think of it, the motivation. If you get a set of parameters just right, then your steel is like, you can sell it for a really good price in the market. You want to achieve like, what are the inputs that get me just this strength level of the steel? And like a production rate, and very little silicon in it. I want to reduce the amount of silicon, but not below a threshold either. You see that? So if you get all those parameters right, then you get really good steel that when you go into the market, you make more money, right? And so the thing you're trying to figure out is, what are the turns of knobs that I have to do in the input of the furnace to produce that steel? And you don't know that information, but who knows that information? The furnace, because it's run over maybe 10 years, it's collected all this data, and now you're like mining that data out. Do you see that? Yeah. So I will, as I said, I'll do a couple of examples for sure, but that's essentially the project. I feel it's a good project. I feel it'll challenge you to like understand some pretty interesting things. And actually, it's a like a different use case than the usual classification or regression. All right. All right. Any other questions before I move on? All right. Yeah. It's iterative. Yeah, it's iterative. So that's right. Exactly. So that's right. But back propagating. Yes, exactly. So yeah, very good. So in the second phase, you create a loop of say, and this is arbitrary, let's say 10,000 iterations. So it starts with a random vector, goes through the model, produces an output, and you compare it to your constraints. Like, is this variable greater than 1700? Is this variable greater than 1900? Is this one less than 150? Right? And then that is expressed as a loss function. And so now that loss function via stochastic gradient descent backpropagates that information to update the weights of the input. Like not weights, but the values of the input. And now this modified input goes in again. Yeah. And produces again. And it keeps going in until it's refined to the point where it starts to produce closer and closer to the desired vector. And when you reach that, so you have to look at like, what is the best vector that it was able to produce in comparison to the requirement? And then you just say, okay, the best that I can do is this one. Yeah. But it's really, the power of it is that stochastic gradient descent it's not random, right? It's really providing the feedback that you need to improve it correctly. All right. So yeah. So okay. So we'll talk more about that next week as I introduce the examples of the topic. For now, start thinking about it. Form your groups for your term project and start thinking of ideas. Right. The easiest is probably, as I said, some industrial thing, maybe some cybersecurity things. The example I'll do is passwords. From there on, if you want to get ambitious, images could be a thing. I haven't really, I've been thinking about that, but I haven't quite arrived at a scenario, but you guys might. So definitely opportunity to do some research and maybe publish it. You have plenty of time. 6 weeks is not difficult, actually. The code is straightforward. That loss is the hardest part, getting that right, but I'll provide some examples of that. Everything else should be doing. Does it have to work? Well, there's got to be some evidence that that the stochastic gradient descent is backpropagating somewhat. It shouldn't stay at random, for instance. You know what I mean? Like, yeah. Yeah, exactly. With ChatGPT, well, in ChatGPT, it was impossible for you guys to build ChatGPT because you know why now. But almost everyone that presented, you could see that there was it was learning, tick token was better. It was if it was veterinary medicine, it was talking about veterinary medicine, things like that. Yeah, exactly. Yeah, right. It's more procedure than actually end result. But that being, and like I said, it's not difficult. The hard part is the loss function. That might challenge you a bit. Okay? All right, great. Anything else? All right, perfect. So I will end this video here as it's just homework and project, very important. Make sure you look at this. And now we can just start our lecture, okay? So, but I will say,